Hi guys, I welcome you to my YouTube channel, Learning Physics with IBM. And today I got the courage to bring you solved past paper questions. And basically this is going to be dynamics and kinematics. This is AS Physics. These are multiple choice questions. That is Physics 9702. And this is going to be kinematics and dynamics. Let this be part one of the solved past paper questions. But before we do that, for those who are new to the YouTube channel, I would like to show you how you arrive at these documents for the past paper questions, for the multiple choice past paper questions. So let's get started. So you go to your, if you go to YouTube and put in Learn Physics with IBM, you go to my YouTube channel. So in any video, for any video you click on, for any video you click on, for example, if I click on this video here, which is force, density, and pressure, for any, of course, this is a list, this is a playlist, but when I go to the video description, when you go to the video description of any of these videos, for example, this was part one, just go to the video description. In the video description, you will see that there are links, and these links open the Google Drive. For example, if I click on the first link, which is this one here. When I click on the first link, then I go to it opens the Google Drive, which shows all the past paper questions which have been assembled in topics. It shows the multiple choice questions, and all you do is just click on these dots here, and when you click on the dots, you will see download. When you click on download, it automatically downloads and goes into your downloads of your computer, so you can open it, you can print. It is free. All you need is to print the document and maybe watch the videos as you learn. Okay, so I think that is fine. So without wasting time, I would like to take you to the document. And me, I already downloaded it, so I will just take you to the document so that we solve the questions. Okay, so here we are. This is going to be part one of solved past paper questions, dynamics and kinematics, or kinematics and dynamics. And if you have downloaded this document, this is how it should look like. So so let's get started. Let's get started. A particle accelerates from rest. The graph shows the variation of the velocity time graph of the particle with time t. Which graph shows the variation with the variation of velocity v with the acceleration a? Remember, acceleration is equal to the gradient. From a velocity time graph, acceleration is actually the gradient. And a straight line means a constant gradient. So this is a constant gradient, but not zero. It is a constant gradient, but not zero. So it means it is constant acceleration. So first of all, we eliminate C because C is showing, first of all, we eliminate C because C is showing that the graph shows the variation of velocity of v of the particle with time t. So this is a graph of velocity against acceleration. It is showing constant velocity as acceleration changes. B is showing that as v increases, the acceleration also increases. A is showing that as v increases, acceleration also increases, but the v is becoming constant with time. Yet we have a straight line here, which means the gradient is constant, so the acceleration is constant. This should give us a straight line. So acceleration should be a straight line. Therefore, the answer is D, which shows that the acceleration is constant. The acceleration is not changing. That's what it means. So for a velocity time graph, the gradient is the acceleration. And if it is a constant gradient, it means the acceleration should be constant. So the answer is going to be D. The graph shows the vertical velocity of a parachutist during the first 20 seconds of her jump. Approximately how far does she fall before opening the parachute. So when we look at the graph, of course, when deceleration starts, that's when the parachute has been opened. So from 0 to around 10, that was an acceleration. Then after 10, the velocity remained constant. That means maybe you might have reached terminal velocity. Then at around this point here, the parachute is opened because we see that the velocity is decreasing, so there is a deceleration there. So I think this is 13. So remember, for distance is actually the area under the graph. So I'll take the area for the whole of this rectangle. I'll take the area for the whole of this rectangle here, and I will subtract the area for the for a small triangle because I just need an approximate value. So I'll subtract the area outside. Let me see. Okay, I will subtract this area here. So I'll subtract this area. Let me increase the thickness. So I'm finding the area of the rectangle, this rectangle here. And I'm going to remove the area of this triangle here so that I get approximately the area of this remaining part here, because this is going to be approximately the distance I'm looking for. The distance has fallen, so that is what I'm going to do. So the area of the rectangle, so the distance has fallen is going to be equal to, the area of the rectangle is 60 by 13, this is 13, 60 times 13, minus, I subtract the area of this triangle here, which is going to be a half, times the base could be, maybe I can say times 60, then times this distance here, I aimed at this point here, which is 7, so times 7. So I'll just press my calculator and check. So we have 60 times, it is 60 times 13 minus, open bracket, 0.5 times 60 times 7. So this is giving us 570. So the answer here is going to be approximately B. So the answer there is B. We just get the area under that part. You could have a different method of finding that area. Of course, you notice that I've not considered this part here. I've not subtracted this part here, but remember this was approximately. So the answer will be B. What is the definition of linear momentum? Of course, we know that momentum, which is normally represented with the letter P, is mass times volume. The linear part is just confusing you, but it's still mass times velocity, not volume. Mass times velocity. So the answer is going to be the product of velocity and mass, which is C. A mass of 0.2 kilograms is suspended from the lower end of a light spring. A second mass of 0.10 kilograms is suspended from the first mass by the thread. The arrangement is allowed to come into static equilibrium. Static equilibrium, of course, that is dynamics. Immediately after the thread is cut, what is the upward acceleration of the 0.2 kilogram mass? Okay. So let's first look at a situation before. Let's just first look at before cutting the thread. Let's begin by looking at before. Before the thread is cut, the resultant, the force downwards, before the thread is cut, the force downwards is going to be for 0, therefore the other one is 0.2 times 9.81 plus, for the other one is 0.1 times 9.81. Before the thread is cut, total downward force is going to be equal to this one. So we have 0.2 times 9.81 plus 0.1 times 9.81 So before the thread is cut, the downward force is 2.943 newtons before the thread is cut. So let's first of all look at after when the thread is cut. Of course, by Newton's third law, if we look at the 0.02 kilogram mass, if you look at the 0.02 kilogram mass and you look at you consider Newton's third law, by Newton's third law, it means the force upwards is still going to be 2.943 initially newtons. So if the force downwards is 2.943 newtons, then the force upwards should also be 2.943 newtons by Newton's third law. But then after the thread is cut, what is the downward force? The force down is on 0.2 kilograms can now be calculated. The downward force on 0.2 kilogram newton is only the weight of 0.2, which is going to be equal to 0.2 times 9.81, which gives us 0.2 times 9.81, which is 1.92. So this is 1.9962 newtons. So initially the force upwards was on the 0.2 kilogram mass before cutting the thread was given by this. But then after, when the thread is cut, then the force downwards on the 0.2 kilogram Newton force is only going to be 1.962 newtons. So the resultant force in this case on that mass is going to be before, which was 2.943 minus 1 point, because this is immediately the upward force must be still 2.943. But then the downward force will change because the 0.1 kilogram mass has been cut off. So this will be minus 1.962, which gives us, what is the difference? 2.943 minus that answer, which is 0.981. So this is 0.981 newtons. That is the resultant. But the question is asking for the acceleration. So the acceleration is going to be the resultant force divided by the mass. And the resultant force is 0.981 divided by the mass, which is 0.20. So the acceleration will become divided by 0.2, which gives us 4.905 meters per second squared. So it means our answer here is going to be A. Of course, this is quite technical, but I want you to notice that before cutting the thread, the total mass downward, the total weight downwards was equal to that. And by Newton's third law, it should be the total weight in the spring upwards. So the total tension in the spring upwards is equal to this before cutting the thread. So immediately when the thread is cut, then of course the total force upwards is immediately still the same as this, but when the thread is cut, then the total force downwards reduces to only be the weight due to this. So the difference between those two is going to be the resultant force that moves the 0.2 kilogram mass upwards. So that's why I found the resultant by subtracting, then obtaining the acceleration from Newton's second law, force is equal to mass times acceleration, where the force must be the resultant force. So the answer is going to be A. A snowflake and a raindrop are in still air. They both fall from rest at the same time and from the same height, far above the ground. The snowflake and raindrop contain the same mass of water. Assume that there is no evaporation or melting. Also assume that for a given speed, the drag force acting on the snowflake is greater than the drag force acting on the raindrop. So I'll use ds for the snowflake and dd for the raindrop. So they have told us that the drag force for the snowflake is greater than the drag force for the raindrop. Which statement about the snowflake and raindrop is correct? So if the drag force is less, they say they both fall from rest at the same time and from the same height far above the ground. And these are in still air. So which statement about the snowflake and the raindrop is correct? The raindrop takes more time than the snowflake to reach terminal velocity. Okay, so to reach terminal velocity, of course, resultant force must be equal to 0. The resultant force must be equal to 0 to reach terminal velocity. But then the resultant force for the drag for the because the snowflake has a greater drag force than the raindrop, then its resultant force is going to be less, and then it means its acceleration is also going to be less. What does that mean? Then it means the raindrop, because the acceleration of this one, okay, the one with the smaller acceleration then takes a shorter, the one with the smaller acceleration takes a shorter time to reach terminal velocity than the one with a bigger acceleration. Let's assume, or let's think about two objects falling, and one is moving faster than the other. The one which has a higher drag force will reach, the one which has a higher drag force means its resultant force reaches 0 in a short period of time. The one which has a higher drag force, it means its resultant force reaches 0 in a short period of time. So that means the answer is going to be A. If when the resultant force gets to 0, we have reached terminal velocity because the acceleration is 0. So I am saying the one which has a higher drag force, because drag force is like opposing the motion. If the object is moving downwards, its weight is downwards, then the drag force is upwards. So FD snow is upwards. So the one with the high drag force, remember that when the resultant force reaches 0, in this case it means the weight is going to be equal to the drag force. So since the snowflake has a higher drag force, it means its resultant force will reach 0 in a very short period of time. And that means it will take a smaller period of time to reach terminal velocity. So the raindrop takes more time than the snowflake to reach terminal velocity. That is very true because the raindrop has a smaller drag force than the snowflake. Okay, so the answer is simply going to be A. Two trolleys are held together on a horizontal surface with a compressed spring between them. When they are released, the trolleys lose contact with the spring. When they are released, the trolleys lose contact with the spring. The trolley of mass 2 kilograms moves to the left. So 2 kilograms moves to the left at a final speed of 2 meters per second. Okay. How much elastic potential energy was stored in the spring? So first of all, let's begin by conservation of momentum. We know that momentum is mass times velocity. By conservation of momentum, initially they were held together and they were initially at rest. The trolleys are held together on a horizontal surface with a compressed spring between them. When they are released, the trolleys lose contact with the spring. When they are released, the trolleys lose contact with the spring. So by conservation of momentum, if one moves to one side and the other is most likely going to move to the other side. So total momentum before is going to be 0. Then total momentum after, we can set to the left positive, to the right negative. So let the speed of this one be u. when they are released. So this is going to be 1 times u. Then because this is, if I say this is moving to the right, this is to the left, so opposite direction I will subtract 2 times its speed, which is 2. So it means u is going to be 4 meters per second. So this one of 1 kilogram moves with a speed of 4 meters per second. So the question is, how much elastic potential energy was stored in the spring? So the elastic potential energy stored is simply going to be the total energy here, which is going to be a half. For the first one is mass is, of course, kinetic energy is a half mv squared. So for the 2 kilogram mass will be times 2, then times 2 squared, the speed was 2 squared, then plus. For the 1 kilogram mass, this is times 1, then times its speed, which is 4 squared. So from my calculator, this is 4 plus, so that is 4 plus 16 over 2 plus 8, which is 12. So the total energy here is 12 joules, which means this is what is stored in the spring. So this is, the answer is D. So of course, the energy stored in the spring is what becomes the kinetic energy of the 2 trolleys. So that's why I got their total kinetic energy when they are moving apart to be actually the same as the elastic potential energy by conservation of energy. So the answer is going to be D. A toy car travels on a circular track at a constant speed of 0.50 meters per second. It passes a point on the track at time t equals to 0 and takes a time 40 seconds to travel once around the track. The magnitude of the average velocity of the car between t equals to 0 and t equals to 20 is v20. The magnitude of the average velocity of the car between t equals to 0 and t equals to 40 is v40. What are the values? What are v40 and v20 and v40? Okay, so I want you to note they said it takes 40 seconds to travel once around the track. That means if it moves around the track, it comes back to the same point. So let's say this is a round track. At t equals to 0, it is here. At t equals to 0, it is here. So after 40 seconds, it comes back to the same point. That means v40 must be 0. So v at 40 must be 0. The velocity at 40 must be 0, or the speed at 40 must be 0 because it has come back to the same point, which means total displacement is going to be 0. So I'm saying v40, v at 40 is equal to 0 because v is a vector quantity. Coming back to the same point, the velocity is 0. So v is 0. Remember, the vector v is a vector. It depends on direction. Depends on direction. And remember, it depends on direction. Actually, it depends on direction of the displacement. Depends on the direction of the displacement, which in this case, which is 0. Which is 0 at time t equals to 40 seconds. So you move from this point, you come back to the same point, the displacement is 0. So it means v at 40 is going to be 0. So v40 is 0, we ignore this one and this one. Then let's check v20. Let's check v20. So remember, the velocity cannot be the same as speed when direction changes. At 20 seconds, velocity cannot be the same as speed when direction changes. At 20 seconds, the direction has already changed. Most probably, maybe it is somewhere here in a different direction. So I'm saying since at v equals to, so that means I'm going to ignore c. C is wrong. Why? Because it is showing that v at 20, v20 at t equals 20 is the same as it is still is the same as speed. So I'm saying v velocity cannot not the same as speed when direction changes. Velocity is not the same as the speed when direction changes, and of course this is the case with part C. So which is the case, and this is the case for a circular track, which is the case for a circular track. For a circular track, a direction keeps changing. That means the velocity will not be the same as the speed when the direction changes for a circular track. That means v at 20 cannot be the same as the speed because the direction is changing. So the answer is automatically going to be A. We ignored D and B and D because v at 40 is automatically 0 because v is a vector quantity which depends on the displacement. Coming back to the same point where we started from, the displacement is 0. So it means at t equals to 40, the displacement is 0. That means v40 is also going to be 0. But then we have eliminated C because velocity is not the same as the speed when the direction changes. Velocity will only be the same as the speed if the direction does not change. But for a circular track, the direction keeps changing. So the answer is A. The graph shows how the velocity v of an object moving in a straight line varies with the time t from t equals to 0 to t equals to capital T. Okay, which graph could represent the displacement S of the object from t equals to 0 to t equals to capital T? I want you to see that at this point here, the velocity is 0. The velocity was increasing, and then it became almost constant, where acceleration becomes 0, and then the velocity decreases back to 0. So increasing, it means, of course, increasing, it must have been going downwards. Here it must have been going downwards, and here it must have been going upwards. That's why it decreases to 0. And so it means at this point here, where v is equal to 0 again, maybe the body is at maximum displacement. So the velocity was increasing, it remains constant, then it decreases. Increasing, remains almost constant, then it decreases. So I want us to notice that from a displacement time graph, the gradient is the velocity. So for this part here, let's start with A. By just looking at the graph of A, I can say that the answer is going to be A because, first of all, for the first few seconds, the curve is of an increasing gradient, which means the velocity is increasing. So this part here is showing that v is increasing. Then around this point here, we see that the gradient is decreasing. At this point here, we see that the velocity is actually decreasing. At this point here, the gradient is 0. So this is almost halfway. The gradient is 0. So here the gradient is 0. So this means here velocity is going to be 0. Then on this part here, the gradient is increasing, but in the opposite direction because it's negative. So it means the velocity becomes negative. So v increases, but in opposite direction. So this part here shows an increase in velocity, When I reach this part here, you see that the line is becoming almost horizontal, so the gradient is decreasing. So V is decreasing, but still in the same opposite direction. So V is decreasing. So when you look at this graph, first part, V is increasing, then it decreases, it becomes constant. So V increases, then it decreases. So V increases to a certain value, then it decreases. Then at this point here, V is 0, almost halfway. Then V increases in the opposite direction. So V is increasing from the graph of S against T, V is increasing. And then V is decreasing at this part here. So here the gradient is decreasing. So the answer is automatically A. I'll need to check B and C. So I'm just looking at the gradient. How do you know that the gradient is increasing when the line is going upwards? The gradient is increasing. When the line is becoming horizontal like this, the gradient is decreasing. When the line is becoming horizontal like this, the gradient is also decreasing. So when the line is becoming vertical like this, the gradient is increasing. So this is increase, increase, decrease, decrease in a gradient. And the graph of velocity of displacement against time, its gradient gives us the velocity. So the answer is automatically A. A good train passes through a station at a steady speed of 10 meters per second at time t equals to 0. An express train is at rest at the station. The express train leaves the station with a uniform acceleration. When it is uniform acceleration, of course, the equations of motion can apply. Of about 0.5 meters per second, just as the good train goes past. Both trains move in the same direction on a straight parallel track, so the equations of motion can apply. At which time does the express train overtake the goods train? Okay, so when one overtakes the other, it means they will have moved the same distance. So at this point of overtaking, they would have covered the same distance. Same distance has been covered. At the point of overtaking, the same distance has been covered. So if that is true, then I'll use S equals to UT plus a half AT squared. So for the first one, S is going to be equal to, of course, they start from rest, I think, an express train at rest. So I'm starting with the express train. For the express train at rest, so this is going to be a half times the express train leaves with that acceleration. So the acceleration is 0.5. Then the time they catch up is going to be t squared. So it means S, the time of catching up, S is actually going to be 0.5 divided by 2. What is that? Okay, let me just leave it as 0.5 over 2 times t. Then remember the other one was moving at a constant speed. A good train passes through a station at a steady speed. So for it, the same distance is going to be 10 times the time t. For the other one, I use the equation of motion. For this one, because the speed is constant, I just say speed times time. That is its distance. Remember, they cover the same distance, which I've called s. So these two quantities should be equal. So I would simply say 0.5 over 2 times t squared is equal to 10t. So 1t cancels out, and you remain with 1t. So t is going to be equal to, I think that is 20 divided by 0.5, which is equal to 40 seconds. So the answer is going to be D. So this is for the other train, which is express. This is express, the express train, and this one is the goods. So for the goods, I just say speed times time because the speed is constant. For the express train, I use the equations of motion because it was moving with uniform acceleration. So the answer is D. A constant resultant force F acts on an object of mass m from time t. What is the change in momentum of the object? So we know that momentum is force times time, or change in momentum is equal to impulse, which is force times time. So without wasting time, this is C. The acceleration of free fall on the surface of planet P is 1/10 of that on the surface of Q. So in other words, we can say G on Q is going to be 10 times G on P, because G on P is a 10th G on Q. So G on Q is 10 times G on P. On the surface of P, an object has a mass of 1 kilogram and weight 1 Newton. What are the mass and weights of the same object on the surface of planet Q? Of course, mass must remain the same, so we ignore C and D. So we know that the weight on P is going to be, because it is 1 Newton, so it is going to be 1 Newton times, on the surface P, an object has a mass of 1 kilogram and a weight of 1 Newton. So the weight is going to be, of course, we know weight is mg. Let me first write the formula. Weight is mg. So for P, the weight is 1 Newton and the mass is 1 Newton, and then times G on P. So it means G on P is going to be 1. So G on P is 1. So let's check for Q. The weight on Q, I'll call WQ, is equal to the mass on Q. Of course, the mass will be the same, times G on Q. Remember, G on Q is 10 times G on P. So I'll simply say 10 times G on P. So I solve these two equations, or maybe by dividing. So when you divide the two equations, you notice that the weight on Q is simply equal to 10 newtons. So the answer is going to be B. When I solve this equation and this one by dividing them, the weight on Q is 10 newtons. So the answer is B. A parachutist falls from rest from a balloon. The variation with time of the vertical velocity of the parachutist is shown. In which region is the force due to air resistance much greater than the weight of the parachutist? Of course, here the speed is increasing. So if the speed is increasing, then remember, when the parachutist is falling, the weight is constant downwards. The air resistance increases upwards. It increases. And they are saying in which region is the force due to air resistance much greater. If the weight is greater than the force due to air resistance, there is acceleration. So this is the part A. There is acceleration. Then when the weight, so here there is an acceleration. There is an acceleration. When the weight is equal to the force due to air resistance, the acceleration becomes 0, so the velocity is constant. We reach terminal velocity Vt. So B, they are equal. So this one is also out. Then at C, of course, we see the velocity now decreasing, so there is a deceleration. So at that point, the force due to air resistance is greater than the weight. Here, the acceleration is negative. A is negative. And you see that it is a negative gradient, so the acceleration is negative and it is much greater. Of course, D is a constant velocity also, because the line is horizontal. It is also terminal velocity, so the answer is going to be C. Two solid spheres form an isolated system. Sphere X moves with the speed 6 centimeters per second in a straight line directed towards the stationary sphere Y as shown. The spheres have a perfectly elastic collision. That is very simple. It means the relative speed of approach is the same as the relative speed of separation. Relative speed of approach is equal to, because the other one was stationary, it is going to be simply 6 minus 0, which is 6 centimeters per second. Then relative speed of separation, RSS, is the relative speed of separation, should also be 6. But note that after the collision, sphere X moves with the speed of 2 centimeters in the same direction as before. So the 6 is going to be as final velocity of say y minus final velocity of x, because the relative speed of approach should be the same as the relative speed of separation. That's why I'm bringing a 6 here. So the 6 is going to be at the speed of y after collision minus the speed of x after collision, which is 2. The word relative means you subtract the velocities. Relative speed of approach was 6 minus 0. Then relative speed of separation should be the velocity of the difference between the two velocities, whichever is bigger. So I just assumed that v for y is bigger. That's why I started with vy minus vx, but it can also be the other way around. So this means v for y is going to be 6 plus 2, which gives us 8 meters per second. So it means the answer is going to be D. If you had done it the other way around, you would still get negative 8, which would just mean opposite direction. If you had said 6 is equal to 2 minus vy, you would still, of course, you would still get a positive anyway. So if you had done 6 is 2 minus vy goes the other side, and no, this will not work. I would say 2 minus vy. I want the highest minus the lowest. I'm assuming that because x was moving with 6 centimeters, if it is now moving with 2 centimeters, then its speed has decreased. So the speed for the other one must be higher. So I started with vy. So the answer is going to be D. Okay. A stone is projected horizontally at time t and falls sorry, a stone is projected horizontally at time t equals to 0 and falls. Air resistance is negligible. If air resistance is negligible, acceleration is uniform or acceleration is constant if air resistance is negligible. The stone has a horizontal component of velocity vh and a vertical component of velocity vy, which graph shows how vh and vy vary with time. I think this was a repeated question. It is repeated here. So which graph shows vh and vy, how vh and vy vary with the stone? Remember, it was projected horizontally. So let's sketch this. It is projected horizontally, like so it moves in that direction. So remember, velocity in the horizontal does not change. So vh always remains constant. There is no resultant force in the horizontal. So v in the horizontal must be constant, which means we ignore b because b is showing v in the horizontal is changing. Okay, so v in the horizontal remains constant because acceleration in the horizontal is always 0. And how about v in the vertical? Since air resistance is negligible, acceleration in the vertical is going to be constant to be 9.81. How do we show that a velocity time graph is having, or how do we show that a body has constant acceleration from a velocity time graph? And the acceleration is not 0. So this means our answer is going to be A, because A is showing VH is constant, and V in the vertical is a straight line whose gradient is constant, meaning a constant acceleration, but the gradient here is not 0. Why is this one not correct? Because here it is showing that acceleration is 0 since it is a horizontal line. A horizontal line means 0 gradient. So here it is showing acceleration is 0. And why not C? C is showing an increasing gradient, which means the acceleration is increasing. Yet if there is no air resistance, the acceleration is constant. D is showing acceleration is increasing, but in the negative direction. Acceleration, because the gradient is increasing, but in the opposite. Okay, the velocity is decreasing, so it means the acceleration is increasing but negative. So this is a negative acceleration because the gradient is negative. So the answer is going to be A, because A shows acceleration is constant. Since air resistance is negligible, acceleration is going to be constant for a falling body, and it will be 9.81. So, and it is not 0. That's why B was wrong. So the answer is going to be A. On the Earth, an object takes time Te to fall from rest through a vertical distance h. On the Moon, the same object takes time Tm to fall from rest through the same vertical distance h. The acceleration of free fall, the ratio acceleration of free fall on Earth over acceleration of free fall on the Moon is equal to 6. Air resistance is negligible. This is very important. Air resistance is negligible, so equations of motion can work. Okay, so what is the ratio Te over Tm? I think that is not very hard. So S is equal to Ut plus a half at squared. So for since they are falling the same distance, I will call it h. And assuming that they start from rest as mentioned here, u is 0, so this will be a half times, now we're on Earth. So acceleration is going to be g on Earth, which is ge. I'll call it ge times the time te squared, if it takes time te. Then on the Moon, the distance, remember, is the same h. Is it on the Moon? Yes, the distance is the same h, falling from rest, so it is a half. U is 0, so it is a half times g on the Moon. I'll put gm. Then the time it takes is given as tm, but it is squared. So I'm going to divide the two equations. Let me divide the two equations, or equate the two equations because they are equal. So I will have that g on the Earth times t on the Earth squared should be equal to g on the Moon times t on the Moon squared, because a half cancels out. Then I will divide it. I will just rearrange this. G on the Earth divided by g on the Moon is going to be t on the Moon divided by t on the Earth, but the other side is squared because these values of these t's are squared. But they told us that the ratio acceleration of free fall on the Earth over free fall on the Moon is 6. So ge over gm is 6. So I'm simply saying that 6 equals to tm over te, but this is squared. But we want te over tm, so we shall get the reciprocal. Or we find the square root of both sides and get the reciprocal. So it means, where should I write now? I've moved like this. Now where should I write? Okay, I'll write this side. So t, okay, I can write here. So the square root both sides, it means root of 6 is equal to tm over te. Then we get the reciprocal. 1 over root of 6 is equal to te over tm. I got the reciprocal both sides. So the answer is going to be automatically B. 1 over root 6 is equal to te over tm. So the answer is B. A ball of mass 0.5 kilograms hits a vertical wall at the speed 12 meters per second. It bounces. If it is bouncing, it means it moves just in the opposite direction. So if one is positive, the other one is negative. It bounces back along its original path with a speed of 8 meters per second. The collision lasts for 0.10 seconds. What is the average force on the ball due to the collision? So we know that by definition, force is the rate of change of momentum. So this is actually going to be m into change in velocity divided by time. So since if we say towards the wall is positive, then away from the wall will be negative. So we get the change, we subtract. So this will be the mass, which is 0.5 into the change in velocity, which is 12 minus negative 8 divided by t, which is 0.1. So I know that people will forget this minus because of the opposite direction. They will just say 12 minus 8. but 12 minus negative 8, which becomes a plus. So this is going to be 0.5 times 20 divided by 0.1, which is 100. So this is 100 newtons, so the answer is going to be D. The upthrust on bubble is X. I think this question will be out because the diagram was missed out, so I'll leave this question out since I don't even remember where I got it. I can't edit it. The diagrams are not indicated here, so I'll leave that question out. Two blocks are at rest on a frictionless horizontal surface. But anyway, we can still answer this question. Anyway, let me leave it since I don't have the diagram. Two blocks are at rest on a frictionless horizontal surface. One block is made of wood and the other block is made of steel. A steel ball is fired horizontally with a speed v at the wooden block. The ball embeds itself in the block and the ball and the block move together after impact. A second identical steel ball is fired horizontally with speed v at the steel block. The steel ball then rebounds back along its original path with speed v over 2. The wooden block and the steel block have equal masses. Okay, that is beautiful. Which statement about the blocks immediately after the collision is correct? Okay. So for this side before impact, of course, the momentum here for the ball is going to be m times v. And this side, when they are after impact, for the first case, of course, after impact, this is going to be m plus capital M. Then I'll multiply, let the speed this side be u, because v has already been taken the other side. So that is for the wooden block. Then for the steel block, so for this one, it means I'll simply say, of course, u1 is going to be, u1 is greater than, is going to be less than v for this one. After impact, u is less than v, of course. So it means when I combine these two by conservation of momentum, mv is going to be equal to m plus capital M times u, which means u is going to be capital M, small m over capital M plus, small m plus capital M. Then I multiply this by v for the wooden block alone. So let me call this one u1 to distinguish it from the steel. Or let me call it u block, u wood, not u1. I'll call it u wood. So this is uw for the wood. Let's check for the steel. For the steel, this side it is mv. So this side it is still going to be mv. What's wrong with my pen? So this side it is mv, and the other side it is going to be because to rebounds, total momentum this side is going to be, for the steel it is going to be m set times, it is capital M for the steel, capital M times u2. We are using capital M for the mass of the steel. Here, remember this was 0, it was at rest, so this is it was plus 0 plus 0, or capital M times 0 because it was at rest. For this one, it is going to be mu2 in that direction. For this one, it is going to be small m because it is the ball, small m, and its velocity is going to be v over 2, but is in the opposite direction. So the sum, one must be positive, another must be negative. So combining the two equations, we shall have mv total momentum before collision equaling to negative m v over 2 plus m capital M u2. That is total momentum after. One is negative, one is the same original direction. So when we combine, or when I collect like terms here, I'll have that small m into v plus v over 2 is equal to m capital M u2. So when we simplify this, or when we combine these two equations, alternatively, when I add v plus v over 2, I think I get, is that 3? V plus v over 2. So this is m into v plus v over 2. What do we get? That is 3v over 2, I guess, is equal to capital M times u2. Okay. So when I make u2 the subject, so u2 is going to be simply equal to, I think that is going to be 3m times capital V divided by 2 capital M. I just divided both sides by capital M. So that will be u2. So compare u2 or u for the steel. Maybe I'll use S for steel, u for the steel. Compare u for the steel with u for the wooden block. Which one is bigger? They're all multiplied by v, but I want you to notice that this quantity here, 3m over capital M, is bigger than this quantity here, which is m over m plus capital M. So it means u2 or us is greater than uw. We are just comparing this quantity here with this quantity here, which I have circled. And notice that this 3m over 2 capital M is bigger than m over small m plus m, which means us is greater than uw. So let's see the answers. Which statement about the blocks immediately after the collisions is correct? Okay, so both blocks must travel with the same speed, not at all. us is bigger than uw. The steel block must travel faster than the wooden block, so the answer is B. us, the speed of the steel, is greater than the speed of the wooden block. How can the acceleration of an object be determined? How can the acceleration of an object be determined? Of course, acceleration is got from a velocity time graph, gradient. So the gradient of from the area under the displacement time graph, that is not acceleration. Area does not really make sense. From the area under the velocity time graph, this is of course displacement. From the gradient of a displacement time graph, okay, I think this is gradient of a displacement time graph. This is velocity, so this is also out. From the gradient of a velocity time graph, so the answer is D. When you have a graph of velocity against time, the gradient is the acceleration, so the answer is D. A sprinter takes time of 11.0 seconds to run a 100-meter race. She first accelerates uniformly from rest, reaching a speed of 10 meters per second, accelerating uniformly. She then runs at a constant speed of 10 meters per second until the finish line. What is the uniform acceleration of the sprinter for the first part of the race? Okay. So initially we shall consider, and because it was accelerating uniformly, we shall consider equations of motion. I don't have enough space here, but I think I'll use, okay, I'll use this space here. So using V equals to U plus AT, I want to find, because she takes a time of 11 seconds to run a race. That means she must have started from rest. So v is 10, initial velocity is 0. Then acceleration, we want the acceleration, I'll call it a, then times time, which we don't know, I'll call it t. So that is the time she takes to reach a velocity of 10 meters per second. And what is that time? So this time I'll call it t1. So t1 is going to be 10 divided by the acceleration a. Then she now runs with a constant speed. I'll use s equals to ut plus a half at squared. But since the speed is constant, then the distance she travels, I'll call it s1, is simply going to be distance, speed times time, which is 10 times the time she takes. I'll call this one t2. Alternatively, no, let me use acceleration. Okay, I'll just use this. It is fine. So S1 is going to be 10 times T2. But from this one, I can get, so this is S2. I needed to find S1 first. Let me first find S1. When there was an acceleration, how much distance did she cover? So if she takes a time T1, which is 10 over A, what was the distance S1 covered? So S1 is going to be equal to UT plus a half at squared. If she started from rest, then S1 is going to be initial velocity 0. That part will be 0, so this will be a half times the acceleration. Remember, the acceleration is 10. Okay, the acceleration, I'll just say a half a times t squared. Then for the second case, when she runs with a constant speed, then I'll call that distance S2. For this, I will just set speed times time since it is constant, so it is just 10 times time, which I'm calling T2. Let this be T1. Okay. But then I know that total distance is 100 meters, and total time, when I add the total time, I should get 11.0 seconds. So I know that S1 plus S2 is 100, and I also know that T1 plus T2, I should get T1 plus T2 is going to be, what is T1 plus T2 is going to be 11. Okay, so I will begin by getting T, or combining the two equations, S1 plus S2. I come up with one equation. So S1 plus S2 is 100. So 100 is equal to S1, which is a half, which is 0.5 times acceleration times T1 squared. Then plus S2, which is 10 T2 squared. No, it is just T2. So it is 10 T2. That is the equation I have. But then note that T1 plus T2 is 11. So it means T2, because I want what is the uniform acceleration of the sprinter for the first part of the race. So I will remove T2. So T2 is going to be 11 minus T1. Okay. So 100 equals to 10 into T2, which is 11 minus T1 plus 0.5 a T1 squared. Okay, I will just use mathematics here to factor out this. I'm just using mathematics. Remember, T1 is 10 over A, so I'll just substitute for T1. So 100 is equal to 10 into 11 minus T1, which is 10 over A plus 0.5 A times T1, which is 10 over A, but this is squared. So 100 equals to, I'm opening the brackets, so this will be 110 A minus 100. I've just opened the bracket and I've taken the A the other side, so there's an A this side. LCM here is A, so I multiply everything by A. This becomes A squared, which A cancels out. Oh, some people may not be good at maths. I will show them exactly what I'm doing. So I'm having 100 equals to, the LCM here is A, so 11A minus 10 over A, which becomes 110A minus 100 divided by A, then plus 0.5A times 100 divided by A squared. So I multiply everything by A. So this side becomes 100A equaling to 110A minus 100 plus, I'm multiplying everything by A, remember? So times A times A times A. So this side it is 0.5 A squared over A squared, which just becomes plus 50. A squared cancels out. So collecting the like terms, when you collect like terms, I think this is going to be 10A being equal to 10A being equal to, I think that is, this is negative 10A equaling to negative 50. So A is going to be equal to 5.0 meters per second squared. So I might have used a longer way, but that is the correct way. So the answer is good. A single horizontal force F is applied to a block X, which is in contact with a separate block Y as shown. The blocks remain in contact as they accelerate along a horizontal frictionless surface. Air resistance is negligible. X has a greater mass than Y. Which statement is correct? The acceleration of X is equal to force F divided by mass X. The acceleration of X is the force F divided by mass of X. The force that X exerts on Y is equal to F. The force that X exerts on Y is less than F. The force that X exerts on Y is less than F. I think by Newton's third law, the answer is going to be C, by Newton's third law, because F is exerted on both of these, on X, and X exerts a force on Y, where Y also exerts an equal but opposite force on X. But remember, the force F is acting on X. So if the force F acts on X, then X will exert a force on Y which is less than F. That means, and that force, the force exerted on Y by X is equal but opposite the force exerted on X by Y. But this force is less than F. If F exerts a force, if F is the force on X, X will exert a force on Y which is less than X, which is less than F. And that means by Newton's third law, the force on Y on X by Y is equal but opposite the force on Y by X, which is going to be less than F. So the force that X exerts on Y is less than F. So this is what makes sense. So the answer is C. I've used Newton's third law. Okay. A car of mass 750 kilograms has a horizontal driving force of 2.0 kilonewtons acting on it. It has a forward horizontal acceleration of 2.0 meters per second. What is the resistive force acting horizontally? resistive force acting horizontally. Okay. So first of all, we shall find the resultant force, which is given by Newton's second law. The resultant force MA should be equal to the difference in the two forces. The driving force is 2000 minus the friction force or the opposing force, which I'm going to call FR. Resultant force MA, the mass is 750, the acceleration is 2, should be equal to 2000 minus FR. So what is FR? So FR is going to be 750 times 2, then minus 2000. So the FR is going to be 500 newtons. That is the frictional force, 500 newtons. But the force, I think 500 is the same as 0.05 kilonewtons, which means the answer is going to be A. Okay, so let part one stop here. Kinematics and dynamics are so much demanding. They require a lot of concentration. So let part one stop at this point. See you in part two. Bye bye.